Welcome to Euler's Stag, a mathematical model where you can literally get a feel for mathematics. It is named after the celebrated Swiss mathematician Leonhard Euler. His groundbreaking work has applications across multiple disciplines, as have the many ideas embodied in the stag. Euler also had to rely strongly on mental visualization as his sight deteriorated throughout his life. The body of the stag is generally smooth. For now, don't try and locate any specific elements. Just explore the smooth surface. You will feel that there are small channels traced into this surface. These lines are contour lines. They run parallel to the board that the stag is mounted on at equal intervals. The distance between the contour lines in the stag's surface indicates the rate of incline or decline over the surface in relation to the mounting board. The further apart the lines, the gentler the slope. The closer together the lines, the steeper the slope. Along some of these lines, arrows are recessed into the body. These are gradient or grad arrows. They are of different sizes depending on the exact angle of incline. The steeper the incline, the larger the arrow, and the more gradual the incline, the smaller the arrow. The arrows point in the uphill direction, where uphill means away from the board. At the highest point on the body, which is furthest away from the board, you will feel a very small pointed bump. This has been placed to demarcate the pinnacle, or the point on the body which is the greatest distance from the board. Just behind the front shoulder of the stag, there is a rib that has been placed on top of the skin. This rib represents a constrained or particular path across the contours. A second very small pointed bump has been placed on the pinnacle or maximum of this path. We call this a constrained maximum. If you now travel to the right of this rib, you will come to the front shoulder of the stag. This shoulder's surface is in the form of a mesh made of triangles. As you feel the surface, you will notice that the triangles are textured. Take some time to feel each in turn. Try not to lift your hands from the surface and instead move from neighbouring triangles. You should feel that no triangles sharing an edge have the same texture. This mathematical feature is a tactile form of a very famous mathematical problem, the four-colour problem. Feeling to the right of the front shoulder will bring you to the longest hair on the stag's neck. This turbulent hair has been used to show the mathematical idea of curl. You will soon feel a large circular section, both cut into and standing proud of the hair. Feel the array of arrows in this section. You should find that the direction of the arrows is changing. Curl can be used to describe the rotation of the arrows. Inserted into the neck of the stag, you can find fields of arrows placed in opposite quarters of the rotational extent of the fur. One of the two quarters shows arrows that increase in size as you move outward in the circle. The other of the two quarters shows arrows that increase in size as you approach the circle's centre. We use these two sets of arrows to represent two vector fields. If the cone-shaped arrows have sizes proportional to their radii, the curl of the vector field is constant. We have a uniform rotation, like a wheel. If the arrows become progressively larger towards the centre and are inversely proportional to their radii, the curl is zero everywhere except at the centre of the circle. This is a rotation like a vortex. A short distance below the representation of curl you have explored sit two models of divergence. Divergence is another measure of the vector field. You should find two circular areas, one raised and one depressed. In the depressed disk, there are arrows pointed outwards from the centre of the circle. One set of arrows increases in size as we move away from the centre, the other set decreases in size. Both are sources like water flowing from a tap and spreading out radially at the base of a sink. The arrows that diminish with radius represent a point source at the centre. The arrows that increase with radius have sources everywhere. The lower half of the front leg that stands away from the board has been transformed into a helicoid. The edges form a double helix. This form is a lovely way of showing minimum surface area. To understand how this is the case, run your fingers along the two outermost edges of the helicoid. These twist opposite to one another. First, imagine that these edges are made from wire and that there is nothing, no surface, in between them. If you joined these two wires with a straight piece at either end and then dipped this structure into a soapy solution, the soap film would take up the interior space to form a helicoidal surface. Soap films always find the shapes with the minimum surface area, as these have the lowest surface energy. The reason that there are subtle horizontal ridges on the surface of the helix that you can feel is indicative of the method with which it was constructed. The helix was made using straight elements, arranged around a central vertical axis and rotated like a spiral staircase. Sat behind the leg is a low relief of the stag's left front leg. This leg has a subtle pattern embossed onto the surface. If you feel very carefully, you will make out a tessellation formed of what are called Penrose tiles. These tiles can completely cover the surface using only one diamond shape and one parallelogram. You should find that the pattern of diamonds and parallelograms doesn't repeat, this being the particularly interesting property of these tiles. Moving back to the body, you can explore the underside of the stag. Under the chest there is a smooth curve with a sharp edge. This begins and ends deep inside the chest, but protrudes below the chest at the lowest point. This curve is called a catenary, and is, for instance, formed by hanging a chain under gravity. We will come across this catenary again when we venture to the head of the stag. Carrying on underneath, you will reach a small, unevenly tiled surface. If you place your other hand directly above this section on the stag's back, you will notice a mirroring, flat-tiled section. You should imagine these as the two ends of a vertical tube with a square cross-section passing through the stag. On the top, we see a flat cross-section and on the bottom a curved one. There are the same number of tiles in both sections, but their areas are different. The Jacobian is a mathematical way of calculating the change in the areas of the tiles for the different cross-sections. On the rear end of the stag sit several features. Feel your way to its haunch and you will notice that a huge section of the anatomy around the hip is missing. The form has been cut away to reveal the top of the stag's femur. The top of this bone has been cleaved away to reveal the intricate honeycomb structure inside the bone. You will be able to feel this subtle texture in the depths of this cutaway. In feeling this small detail, you will have to dodge the large cone-shaped protuberance. You will notice that this structure emanates from the fine bone texture of the femur. This is because it is, in fact, depicting the magnification of this honeycomb structure in 3D. You will notice the structure growing in scale as your hands move from the point of the cone to its flat face. Explore this structure as best you can with your fingers, and notice that in certain places your fingers can make contact through the structure and hook around it. Small three-dimensional volumes like this are used in integration, specifically in the method of finite elements. The concept of this structure comprises of many segments that fill a given space entirely. A nice way to imagine this is to picture a room filled with stars, all suspended at random points in the space within the room. Now picture all of these stars expanding. They may expand at different rates, they may not. Eventually, however, the whole room will be filled with a froth of sparkling bubbles that have expanded to every nook and cranny, pressing against one another and leaving no space left to fill. The honeycomb texture that you can feel is a version of the same concept. Each bridge of bone marks the joining point of these many three-dimensional elements. Moving below, you will feel the surface of the stag's muscle. The dermis has been removed so that you can feel the striation of the musculature. Imagining these striations as the infinitesimal steps through the path your fingers take, try and find the artery that stands proud of the muscle. This is a path like one we might take when doing a line integral. This can be broken down into many small steps and is what the muscular stria represents. You will feel this artery disappear under the hide. There are no more mathematical features of this leg, so you can make your way to the leg behind it. A nice follow-on from the concept of three-dimensional elements that you just came across is a Voronoi pattern. This can be found on the low relief of the stag's rear left leg. Subtly embossed onto the surface is a two-dimensional pattern of lines creating tiles of different shapes. The tiles are constructed in the following way. A set of points was drawn on the leg marking the positions of the stars in the constellation Scorpius. Lines were drawn to near neighbours of each star and perpendicular bisectors drawn to these lines. These bisectors intersect to form the vertices of each tile. The star points on the leg have been removed. Can you imagine where they are? As you reach the tail, you will notice that once again it is represented by a specific mathematical shape. This one is called a deform. Deforms come in many different shapes and sizes, but all have one property in common. They are formed by joining together the edges of two shapes which have the same perimeter length. In this case, two ovals with this property have been joined together. The ovals form curved surfaces with only one principal curvature. Comparing the differing orientations of the ridges along each oval will tell you to what extent the ovals have been misaligned. This misalignment means that joining the ovals leaves a hollow interior and creates a three-dimensional shape. On the head of the stag, you will find that one half is naturalistic and the other is an abstract form called a Klein bottle. First, get a sense of the shape of the whole form. Now find the broken edge of the form and feel inside. You should find the exterior of one tube running through the interior of another. Now feel inside the abstracted nostril with your other hand. This is the interior of the smaller tube you've just felt. Notice that the interior of the smaller tube becomes the exterior of the larger tube. The Klein bottle is a finite two-dimensional surface with no boundary, but with no inside or outside. The broken edge is not a true part of the bottle, but is forced upon us when we try and make a three-dimensional model of the form. After exploring the Klein bottle, please feel free to touch the other side of the head of the stag to orientate yourself with its natural anatomy before moving on to the antler. The antler of this stag is a representation of branching processes. You can think of each branch representing a choice, like going left or right. We label each branch by listing that choice together with all previous choices that brought us to that point. We start the labelling at the base of the antler. The labels feature one or two vertical dashes that represent the two choices at each branch, and dots to represent the movement to the next branch. Near the base of the antler, you will come across the ear. The ear has also been created from a mathematical shape. The ridges that you can feel on either side were actually a series of chains. These had been hung under gravity and set so that they retained their curvature. The space between the offset chains on the inside and outside of the ear was then filled to create a solid surface and thickness. The curve described by these chains is called a catenary, a concept you've come across once before. Interestingly, if you were to hang a chain on any planet, this catenary remains the same, provided there is some gravity. It doesn't affect the catenary, even if there is only a weak force. I hope you've enjoyed this short tour of Euler's stag, and it has encouraged you to further investigate some of the ideas and concepts that it embodies.